Hello, so I'm going to try some moles and molar mass questions, and let's start on the first one. The molar mass of strontium, which has a symbol of Sr, is 87.62 grams per mole. Calculate the number of atoms in a 67.5 milligrams of strontium. Write your answer in scientific notation using three significant figures. So, to find out how many atoms there are, we would want to convert it into amount of moles. Because when we convert it into amount of moles, we can use the Avogadro number, which will help us to convert the amount of moles into how many atoms there are. Because simply talking, Avogadro number would because um in a very small piece of an some type of compound or element there are a bunch of atoms. So what we want to do is to make the number smaller by making a unit of mole. Therefore we can calculate things easier or more conveniently. But when we want to find the amount of atoms, we would want to convert it into moles and then into amount of atoms. So the Avogadro number would give us, for example, there would be the we are going to have a Avogadro number amount of atoms in one mole, or Avogadro number in one Avogadro number of compound, molecule, anything like that in one mole of compound, molecule, anything like that. It depends on the context. In this context, we are dealing with elements, so we're going to find atoms. So we already identified that we want to figure out what would be amount of mole of strontium when we have 87 or when we have 67.5 milligrams sample of strontium. So let's do that. How are we going to find amount of moles from 67.5 milligrams of strontium? We're going to use the molar mass, because the molar mass connects mass and mole. That's what molar mass is. Because if we kind of look at the unit of molar mass, it is in grams per mole. So we can kind of come up with a formula by ourselves. So usually the variable for molar mass would be the big M, and the big M would equals to the mass, which is usually symbolized with a small m over the amount of mole, which is grams per mole. That's what grams per mole means. It is grams per mole, mass over mole. So mass would be the small m, and usually the variable for mole will be small n. So molar mass is equal to m over n, or big M. Big M is equal to small m over n. So what do we have? We have big M, which is 87.62, and that will equals to, I will omit some units here because for the sake of space. So we have 87.62 is equal to mass, which is 67.5 milligrams. We want to make it into grams because when we look at the molar mass of, or when we look molar mass of strontium, we see that it's in grams per mole. So it's in grams. But currently we are in milligrams. So we want to convert from milligrams into grams. So how are we going to do that? So one important thing we should know is 1 gram is equal to 1000 milligrams. So when we want to convert from milligrams into grams, we would want to divide by 1000 because we're going up in the unit. Grams is bigger than milligrams. 1 gram is bigger than 1 milligrams. It is 1000 times bigger than milligrams. So when we want to go from milligrams up to gram, we would want to divide by 1000. If we want to go from grams into milligrams, we would times it by 1000. So let's do that. We're going to have 67.5 milligrams and divide by 1000. And that should give us the answer that we get. So let's put in my calculator right here. 69 or 67.5 divided by 1000. And that should give us 0.675. It should show down here. So that should be 0.675 milligrams. So 87.62 is equal to 0.0675 over n. So how are we going to find n? And the way we can find n is we're going to manipulate this formula a little bit. So we have m is equal to m over n. How are we going to, we want to find n, so we want to isolate n by itself. So how are we going to do that? We're going to times n by both sides. So when we times n on both sides, we're going to cancel the n on of the fractions, cancel the denominator m over n. Therefore, we have n times m, and that should be equal to mass, which is m. We are not looking for mass, we are looking for amount of moles. So one more step is we want to cancel the m that's being stuck with the n. So m over here, big M, molar mass, and divided by both sides by m, big M. So now we're going to cancel the big M or the molar mass, and now we have n by itself. N is equal to m over m, or mass over molar mass. So let's do that. So in this case, the molar mass or the mole of 67.5 milligrams sample of strontium, we're going to take the mass and divide by the molar mass. So we have the mass of 0.0675 and divided by 87.62. And if we do that, that should give us around 7.7 something to the power of times 10 to the power of negative 4, which you should be able to see in a second. That should be the next thing you should be able to see. So that would be the amount of moles that we have, 7.7037200612 times 10 to the power of negative 4. Awesome. And now we're going to find how many atoms is in this amount of mole. And one thing will be helpful for us would be the Avogadro number, and which the question does give to us. That will be 6.022 times 10 to the power of 23 mole per mole to the power of negative 1, or the inverse of mole, or 1 over mole. So what it's talking is the Avogadro number, let's say A, is equal to amount of is 1 over mole, and that 1 is depend on the context. In this context, we are using elements, so the end result will be atoms. So, and that's what we want to find, atoms. And we have the amount of moles of an element, which is strontium, and we want to find how many atoms of strontium is in 67.5 milligrams of strontium. So we have A, which is Avogadro number, is equal to 1 over mole. And that mole is practically the variable n that we started with. So that we A is equal to 1 over n. So we have A is a constant Avogadro number that will always be 6.022 times 10 to the power 23. And n is the number that we can find, that we already find, which is 7.703720612 times 10 to the power negative 4. So to find 1, and 1 is depending on the context really. In this case it is atoms, so let's change it into atoms, or small a. Let's make small a would be the variable for atoms. We want to find how many atoms are there, and the way we can find atoms or isolate A, small a by itself, is to take 2 times n on both sides to cancel the n. So what we will have is n times A is equal to small a. So n times Avogadro number would equals to the amount of atoms. So we take the amount of moles times it by the Avogadro number to get amount of moles. So let's do that. So we have the amount of moles in our calculator already. And the only thing we need to do is to times it by the Avogadro number, which is 6.022 times 10 to the power of 23, and it gives me an answer which is 4.63 4.631805 something so on. You should be able to see it shortly. There we go. So that should be 4.63918055 times 10 to the power of 20. That should be the amount of atoms in 67.5 milligrams sample of strontium. And we need three significant figures. So we are going to round it to 4.64 because the number behind it would be 9. We want to round it up. So 4.64 times 10 to the power of 20. And there we go. That will be the right answer. Next question. Okay, using the information in the table, calculate the number of moles in a 5.73 kilograms sample of lactic acid or C3H6O3. So we are provided by the mass and we want to find how many moles would it be. So to find the amount of moles using mass, we need molar mass. So we need molar mass of lactic acid. But currently we don't have any molar mass for lactic acid. What we have is the molar mass of hydrogen, carbon, and oxygen, which have 1.008, 12.01, and 16 grams per mole, respectively. But we can use those numbers to calculate what will be the molar mass of lactic acid. And the way we can do that is we're going to take each of the molar individual elements molar mass and add it up. So in lactic acid there will be C3H6O3. It means that every molecule of lactic acid, it will have 3 carbon, 6 hydrogen, and 3 oxygen. So keep that in mind. We're going to have C3, which is 6 carbon, so we're going to take 12.08 or 12.01 and times it by 3. And the same thing will happen with hydrogen. So we have 1.008 grams per mole for hydrogen, and we have 6 of them, each 6, so we're going to times it by 6. And the same thing happens for oxygen. We have 16.00, and we times it by 3 because we have C3H6O3. We have O3, which means 3 oxygens. So let's do those calculations. So 12.01 times 3, and then 1.008 times 6, and 16.000 times 3, and that should give us 3 different values, and I will show them in my calculator right here. Perfect. So we have 12.01 times 3, that will be 36.03. 1.008 times 6, that will be 6.048. And 16.00 times 3, that will be 48. And we would want to add those 3 together, because the lactic acid, those 3 numbers would make up the molar mass of the lactic acid, because currently we have each of the individual molar mass of each of the building blocks of element, or the building block element of lactic acid. So you want to add it up. So that will be 36.03 plus 6.048 plus 48. And that should give you an answer about 90.078, which I would show it shortly. There we go. That will be 90.078. And that will be the molar mass of lactic acid. So let's put it in. So the molar mass of lactic acid, or usually the big M, which symbolized by a big M, is equal to 90.078, and unit would be grams per mole, because at the beginning we are using grams per mole and we don't change it any time in the process, so it will stay grams per mole. So the molar mass will be 90.078 grams. We need to find the amount of moles, and what the other thing we have is the mass. The mass in this case would be 5.73 kilograms. But if we kind of have a look at the unit of molar mass, we have grams per mole. So we want the mass to be in grams to compatible with the calculation we're going to make. So we would want to make 5.73 kilograms into grams. 1 kilogram is 1,000 grams. So to convert from 5.73 kilograms into grams, we would want to times it by 1,000, and that should give us 5,730 grams. Wait. So if I show it on here, if we times it by 1,000, that should give us 5,730 grams. So now we have 5,730 grams. And the other thing that we have is the molar mass. And if we kind of recall from the first formula that we kind of make, big M is equal to mass over N, which is mole. Because if we look at the unit grams per mole, it is mass over mole. Grams is mass, mole is the amount of mole there are. So mass over mole. So we have M, which is big M, which is molar mass, which is 90.78 grams per mole, and we have mass, which is 5,730 grams. We need to find mole. And we can manipulate this formula so that we can times N on both sides. So if we times N on both sides, we cancel out the N, and what's left is N times M is equal to M, but we still want N by itself because we want to find N, which is the amount of mole. Therefore, we want to cancel the big M on both sides by dividing by M on both sides. So what we will have is N, or the amount of moles, is equal to mass over molar mass. So let's do that. So we have the mass of 5,730 and we have the molar mass of 90.078 grams per mole. And if we do that calculation, that should give us the amount of moles in 5.73 kilogram sample of lactic acid. So if we do that and calculate that, okay, so that should give us about 63.611, so on and so forth. So that will be the amount of moles of 5.73 kilograms sample of lactic acid, which is C3H6O3. So we need 3 significant figures, so that will be 63.6 mole of C3H6O3. There we go, perfect. Okay, let's do the next question. So the molar mass of sulfur is 32.06 grams per mole. Calculate the mass in grams of a sample of sulfur containing 2.01 times 10 to the power 24 atoms. So we are being provided with a amount of atoms, and we want to calculate what will be the mass of it. So if we can recall back to the first question that we did, we start with the mass and go into how many atoms there are. Now we start with atoms and we want to find out how much mass would it be. We would do the same thing, almost the same thing, very similar thing, but in reverse. So if we can recall, the Avogadro number is equal to 1 over mole, or 1 over N, because N is usually the variable for mole. And we have Avogadro number always ready because it is a constant. It is 6.022 times 10 to the power 24 or 23. And practically we can look at here because it's provided to us. There we go. It will be 6.022 times 10 to the power 23. So using this knowledge, we're going to find out how many mole would it be. So with this one, we already discussed that it can be anything depending on context. In this context, that will be amount of atoms, so that will be 2.01 times 10 to the power 24. Because the 1 can represent anything, that is atoms, molecule, anything. And by using the Avogadro number, we would find the amount of mole of that element so far. So we have A, which is 6.022 times 10 to the power 23, which is the Avogadro constant or number. We have amount of atoms ready, 2.01 times 10 to the power 24 over n, which is the amount of mole. And we need to find out how many mole would it be. And the way we can find this is to isolate n by itself to find out how many mole would it be. So we have 2.001 times 10 to the power 24. We want to find what n is equal to b, so we would want to times n on both sides. Times n on both sides. That we cancel to. And what we have is a times n is equal to amount of atoms, 2.01 times 10 to the power 24. And we want to also cancel out the Avogadro number on both sides, or divide by the Avogadro number on both sides to cancel out the Avogadro number on the left side to isolate n by itself. So now we have n is equal to 2.01 times 10 to the power 24 divided by Avogadro number or constant 6.022 times 10 to the power 23. So that should be the way we figure out the mole. So if we put that in our calculator, so we have 2.01 times 10 to the power 24. And then we divide it by the Avogadro constant, which is 6.022 times 10 to the power of 23. If we do that division, that should give us the amount of moles there are, and I should be able to show it to you. There we go. That will be around 3.33776151 or 541. So that will be amount of moles. So now we have amount of moles ready. The way we can, and the last step we want to do is convert from mole into mass. And one thing to note is the thing that connect mass and mole together is molar mass. So if we use the molar mass, we can figure out mass or mole or anything by knowing molar mass and the other thing as well. So using the unit of molar mass, grams per mole, we can make up a formula for ourselves, which is M, big M, which is usually symbolized for molar mass. That will be equals to mass, which is grams, and divided by the amount of mole, which is N. And we need to find M, which is the mass, small m. And the way we can do this is to cancel times n on both sides, to cancel the n. So now m is alone, and we want m to be alone, or mass to be alone. So that's what we want. N times m is equal to mass, or mole times molar mass is equal to mass. So let's do the same thing. We have the mole, which is 3.3377615141. In our calculator, we're going to times it with the molar mass, which is 37 times 32.06, And if we do that calculation, we're going to find that will give us the mass of sulfur. So if I'm going to show it in a second, That should be 107.008635. So our final answer will be in three significant figures, that will be 107 grams. And that should be it. There we go. Perfect. Let's do our last question. Moles and molar mass. We have element F, which is fluorine. Molar mass is 19 grams per mole. And strontium, which is Sr, which has a molar mass of 87.62 grams per mole. And one thing we want to find is the formula unit of it. So if we don't know what the formula unit is, there's a explanation of what is a formula unit. So formula unit is the fundamental unit of an ionic compound. We can calculate the number of formula units in a sample of ionic compound in the same way that we would calculate the number of atoms in a sample of element, or the number of molecules in a sample of molecular compound. Perfect. And I think we would need this number as well, the Avogadro number. Perfect. So practically we need to convert from mass into formula units, or practically the atoms that we want to find on the question 1. So we're going to combine multiple scales together. We're going to combine the scale from question 2, where we want to find the molar mass of a molecule or a compound. And then we want to use the scale from question 1 and question 3, where we convert from where we're going to use Avogadro number to convert from mole into atoms, or in this case formula unit, or vice versa. So let's do that. So we have the mass ready, 33.8 grams of strontium fluoride SrF2. But we don't have the molar mass of strontium fluoride. And if we recall from the question 2, the way we're going to find the molar mass of strontium fluoride, we're going to add up all the molar mass of each of the individual element and add up. So we have F is equal to 19 grams per mole. We have 2 fluorine, so that will be 19.00 times 2. And we have strontium, which is 87.60. And we would want to times it by 1, because or just times it by 1. Yeah, because there's only one strontium. And if we do the expressed equations that that I have written down and put into our calculator, that should give us the individual element molar mass, and later on we can add it up and to make it into the molar mass of strontium fluoride. So let me show you the molar mass of each of the element. So for fluorine, that will be 19 times 2, that will be 38. And for strontium, that will be 87.62 times 1, that will be the same, 87.62. And to find the molar mass of strontium fluoride, as we recall from the question 2, we would want to add those two together. So those two, so 38 plus 87.62. And if we put it into our calculator, that should spit it, that should give us a number, which is 125.60 mole, or grams per mole, I mean. That will be the molar mass. So we have the molar mass of strontium fluoride. That will be 125.62 grams per mole. And I think we can safely ignore those two above. I don't think we're going to use it anymore. So that is the molar mass of strontium fluoride. Now, so let's make up the formula once again, like we did in, I think, question 1, 2, and 3. So we have molar mass is equal to mass over mole. If we look at the unit, grams per mole. Grams is mass. Mole is amount of mole. So mass over mole, or m over n, small m over n. And we can fill those things in. So we have mass, or the mass is 32.8 grams. So that will equals to 32.8 grams. And then divided by n. And that should give us 125.62 grams per mole. And we want to isolate n by itself. And the way we can isolate n by itself, like we did several times before, we're going to times n on both sides to get rid of the fraction and cancel out the molar mass on both sides to isolate n by itself. So now we have mole n is equal to small m mass over big M, molar mass. So the mole is equal to mass over molar mass, 32.8 divided by 125.62. And if we do that calculation, do that division on our calculator, that should give us the amount of mole. And if I show it right over here, that will be 0.2690654.354. That will be amount of mole. And what we need one more step to do. So if we can recall, if we have amount of mole, we can convert it into atoms. In this case, formula unit, anything that depending on the context with Avogadro number. So if we take this number and times with Avogadro number, we would make the formula units or atoms like we did in question 1. If we didn't remember what question 1 is, we have a mass and we want to make into how many atoms there are. And in the way we figure out the Avogadro number unit would help us figure out what we want to do with mole and Avogadro number. So let's do it one more time. So Avogadro number, let's symbolize it with a big A. And a big A, or Avogadro number, is equal to 1 over mole, or 1 over n. And we said before that n or 1 can be anything in context. In this case, that will be formula unit. So 1 will be formula unit. And n would be the amount of mole. And A would be Avogadro number. So to figure out the formula unit, let's say formula unit will be F. Not to confuse with force in physics, that we have that's the variable that we make up with. So take it as a grain of salt. So we have Avogadro number is equal to F over n, or formula unit over mole. And we want to find amount of formula units, or how many formula units are there. And the way we can do this is to times n on both sides, times n on both sides. That will cancel out the n. And what we have left is F by itself, which we want to have because we want to find out how many formula units there are. When we want to find a variable, we want to isolate the variable by itself. So in this case, we have F by itself. So we have this the result we want to have. So we have n times A is equal to F. Mole times Avogadro number is equal to the formula units. So we have the mole, which is in our calculator right now, 0.269, so on and so forth. And times it by Avogadro number, which is 6.022, times 10 to the power of 23. And that should give us 1.632, so on and so forth. I can show it to us. Give me a second. So that should show it. You should be able to see it right now. So that will be 1.6203, so on and so forth, to the power of 23 formula units. So if we put it in, 1.62, three significant figures, times 10 O times 10. Let me check a little bit. So times 10 to the power of 23. That should be the final answer because it's on our calculator. So if we have a check on this, there we go. That should be all of them. Thank you very much. Okay. I hope this video is helpful for everyone. And yeah, good luck on any moles and molar mass question. And yeah, good luck with chemistry.